Hello again. We resume the lecture on architectural design. So just to remind you very quickly, what we have said so far is that the architectural design of software systems, or indeed all types of information systems, is about deciding the major components or subsystems of a complex system, and this is necessary for you to have a discussion, a good discussion, an informed discussion with your stakeholders, clients, and possibly even users, as well as with the technical team of engineers or analysts and designers who are making these decisions. So it's a basis for a debate so that people can synchronize their view or their views on what system they're going to have. It's also important for documentation purposes. It's how you document your design decisions at the global level, and it's the artifacts or a set of artifacts that you pass on to the designers who are going to design the more detailed implementation of each of these components. So the components still need further design of their details as to start implementing or coding after that. So it's really important to bear in mind these benefits of architectural design. One very important benefit that I'd really like you to grasp is that the architectural design phase is your opportunity to build in or design in the non-functional properties that we mentioned before. Things like performance, security, robustness, availability, etc. Your design decisions here will guide or determine how these attributes are realized later on in your system. So it's your opportunity here to reason about how your system is going to be resilient to changes, resilient to maybe disasters or adverse conditions, errors, hiccups, disasters, whatever. Yeah, as well as things like performance, of course, and being able to satisfy certain requests in a reasonable amount of time or at the required level of performance. Okay. Last time I also started discussing what we called generic architectural template, things like the MVC, the Model View Controller, and how that might work. And in general, we need to remember that these architectural patterns, I actually prefer to call them architectural styles, are generic solutions that have been proven to be useful for certain types of applications. So like very general patterns at the architectural level. That's why I prefer to call them architectural styles. And one of them was the MVC, which is again really can be like the general case of the or the specialist case, if you like, of the layered architecture. And I mentioned how these layers separate concerns, and this means that once one of these layers changes significantly, you don't have to modify or interfere with other layers, or at least you minimize the effect of the change as long as the interfaces have not been changed. Yeah, between one layer and the one next to it. So here we're teasing out the areas of change, we're separating them from each other so that the change does not have a big ramification on the system and does not cause you a great deal of effort and cost and delay until you come out with this particular change. I mean, finish it and make it available to people who are using the system. Right. Okay. So back to the architectural styles. One popular architectural style, or one particular architectural style, is the repository architecture. And let me show you a diagram here. it looks something like that. So would be an abstract representation of the repository architecture. You've got a number of modules or subsystems, all accessing and modifying a single project repository. The project repository could be something like a database, for example, or in some AI systems that we call blackboard systems. So the central thing is like the blackboard where all sources of manipulation or agents or problem solvers cooperate on a single entity that sits in the middle that everybody can access to. And this is in contrast to every agent or every subsystem or every component keeping its own copy of the same data, which obviously would be very inefficient. They could go out of sync. So the copy of the repository that each, or the copy of the database or file or whatever that every subsystem is keeping will eventually get out of sync. So you have inconsistency because the values or the images of these bits of data would be different throughout the system. So one solution is to say, okay, if the volume of the data is large and all agents need access to it almost more or less simultaneously, so I could not really pipeline it because we can all access the data at the same time, then this is perhaps a suitable architectural start for building this system. So it's also a very good way of exchanging data. So the shared data is set or is held in a central database or repository, and all subsystems have access to it. And each subsystem maintains its own database. That would be the sort of undesirable condition here, yeah? Because, I mean, obviously sometimes you do this, it depends on your performance criteria. Maybe you can do this for performance purposes, but obviously there's the problem of keeping all these copies of the data being consistent, or every subsystem would pass the data that the other subsystems need explicitly by way of maybe calls or data exchanges interfaces of some kind of another. But obviously when the data gets too large, quite often people prefer to use the repository model. I'll leave you to read the documentation of that style. As I said here, I prefer to use the term style rather than pattern, because we'll have look at more detailed patterns later on, or patterns that operate more at the individual component level. Yeah, the individual component level can logic or organization can also be described as a pattern. Yeah, software pattern. But here at the level higher up than the single component of subsystems, here we're describing how these subsystems are related and organized, or these components are related and organized. I hope you get the idea about the global high level and the more detailed level. If there are any problems with that, please ask me during the lecture. So I'll leave you to read that. And let's move to this. Another style is the client-server architecture. I'm sure you've heard about that on many occasions. So here we are distributing the system in a way that separates the data or distributes the data away from where it needs to be accessed and manipulated. Yeah, so you have one or more standalone servers which provide specific services such as printing, data management, etc. Now, the concept of server really, I don't know if you've looked at that carefully, but the concept of server is that I have a specialized or a dedicated a machine or software, yeah, a dedicated component that sort of specializes in giving a particular service, like printing, for example. So you could have a print server, or data management server, or a security server, or a mapping server, like what you have in the DNS server in internet systems. So it gets specialized in maintaining this data, providing the server, and other clients around it can access these services and call upon them. Yeah. And that has certain advantages, as we'll see. But obviously, you need some kind of data network. Yeah, it could be local, it could be wider wider area network, but you have some means of communication between the clients and the servers. Yeah, so you need some kind of data network. Now, most systems most client-server systems are implemented as distributed systems connected using internet protocols that you know about. Again, there's like a template that describes this architectural style, client-server style, and here's a way of representing it visually. So if you have like a film library, so you have a number of clients that connect or communicate with the servers by some data connection facility or infrastructure, and those guys can access a number of servers that are available online or using some kind of connection. So you've got a web server, you've got a picture server that would serve photos, you've got a video server that would serve film or films. Here's a catalog server that would provide a library catalog. So this is like an indexing server service for these other servers. Okay. Now, what advantage does that have? There's a number of advantages. One of them is that the clients can be sort of be relieved from certain responsibilities for maintaining a large amount of data. And those servers can be specialized in serving data, protecting, replicating, controlling access maybe as well, providing backup services. Yeah, this is one fantastic or important service when you have a dedicated server for your data, is that the server worries about providing backup and recovery services in case of there's a malfunction or there's a breakdown or there's a disaster or something. Those clients do not have each to worry about how the data maintained in the server is going to be kept in an integrated or high integrity fashion. Okay. Yeah, let's just yeah. We'll see some more examples of client server architectures. One more architectural style. Okay, let me show you how it looks like first, very quickly. In the file server architecture, we've got like a number of processes that are connected using some kind of connections that we call pipes. So these processes are sort of passing whatever object they're manipulating or processing onto the next service. So here you've got the object or the data or the file or the list or whatever of payments that this process is doing something with them. And based on this identification, it either chooses this route, yeah, so it determines which would be the next transformation, yeah, or filtering process, and or this other one. So if the payment is paid, so you issue a receipt. That's the logic of the system. If the payment is due or overdue, then you issue a payment reminder. So you pass the data on to the next transformation process, which is issuing a payment reminder. If you recall the data flow representation or the data flow models, it's very similar to data flow model, where we have processes, and these processes are interacting by passing the data on from one process to another. So this is called pipe and filter architecture, and it's quite old, as old as the Unix system, where we have a Unix command like that. So this is to list the contents of the invoices directory, and the grep command, grep is short for global regular expression print, and this is used to search text and fish out certain strings or certain values you want from that. And then after you've selected or sorted or searched the file for this term, then you sort it, so it's passed on to a sort process. So actually, these are the pipes. These vertical lines represent the pipes, and these are the filters. These are the processes are the filters. So grep is the one process for searching the text file, and sort is another process that would sort them. Yeah. So these types of applications This is a typical Unix command, and basically you have this view of data being passed from one process to another. So essentially, the pipe and filter architecture type, I don't even want to call them as much as style, because anything can be represented as pipe and filter. It's just straightforward transformation processing, sequential transformation, or sequential processing. So the function transformations here process their inputs to produce certain outputs, and this is one way of referring to them, pipe and filter model. Now there are many variants of this approach when you have like a sequential set of transformations. Sometimes people call it this is batch processing or batch sequential processing model, which means that things go all together. It's not like an interactive thing where a user enters one input at a time and receives an output or response for the input they have provided, but it's like a large batch of transactions that are processed all together. So a lot of these transactions, a lot of these instances are processed together, and once they're processed in one stage, the results are passed on to the next stage. Yeah, so it's sequential. It happens in a series. Yeah, that's why we call it a batch sequential. It's an old model. It's been there for ages. It's particularly useful or extensively used in a data processing system, like for example the transaction processing at the end of the day in banks. This is the sort of processing that happens to them, where all the transactions, all the withdrawals, etc., are run through some maybe summarizing or analyzing software to draw certain conclusions of them. Okay, so then this kind of style is not really ideal for interactive systems. It's not suitable actually, because in an interactive system, the users expect an immediate reaction to their input or the request. Yeah, it's interactive. So the user supplies an input or a command, and they expect a response more or less instantaneously. Because an interactive system control strategy is based on events. So the system has to respond to events like a piece of data or a mouse click or many selections. Right, and these are so typical examples of part of filter architectures like Unix shells, like in this example, and also in distributed system, systems will have every instance of the processor is basically processing a piece of data or a bundle of data, and they can pass this results. Right. So here's a visual. Here's a visual of how this might work. I'm sure we that before. So basically, it's like sequential or sequential set of steps to process data across a number of more or less sequential processes. Right. Application architecture. So let's go like one more level down. In application systems are meant to satisfy certain organizational needs or requirements. Quite often, businesses do things in a common way. The general logic is similar. So the application systems tend to have common architectures because businesses have so much in common. And these are like repeating patterns keep happening again and again. So common architecture would reflect what the application is supposed to be doing. So generic application architecture is one type of software system that may be configured and adapted to a system that meets specific start from a generic template and you adapt that to suit a particular domain. And you can think of some very typical systems like maybe a system would have the solution to authenticate credit card transactions. Many businesses, many banks would go about it more or less the same way, or the main sort of card issuers would recommend or impose or give them a generic application architecture that all banks would more or less follow. Things like air ticketing, airway ticket reservation. Again, this is a fairly stable application that would have a generic application architecture that could be adapted to particular companies, but there's a lot that is in common that we capture in a single application architecture. So the application architectures become a starting point for architectural design. It also forms a kind of design checklist. It's really like a reuse of the generic design. So instead of reinventing the wheel, so you're reusing an existing architectural design, and you're adapting and you're modifying it as may be the case for a particular organization. It also becomes a way of organizing the work of the development team and dividing the tasks amongst them. It's also a way of achieving, and before that, assessing various components for reuse. Yeah, said the application architecture is a common way of reusing generic application designs instead of you having to do it from scratch every time. It also provides you with a vocabulary to talk about application types. Like we say, oh, this is a client-server architecture, this is a two-tier architecture, this is a three-tier architecture, this is an n-tier architecture, and so on. So let me just go through these slides, which actually I've gotten from a different textbook. Okay, now the generic components or generic parts of applications that we typically find in lots of applications are generally or commonly have things to do with presentation. So we put them in a layer. Yeah, a layer would include related components or elements together. So there'd be a layer, and they share common things like they share their orientation. Maybe these presentation components are oriented towards the user, and they change maybe frequently together, or they're related in terms of the speed of change. We have the presentation logic layer, which is the processing that must be done to generate the presentation itself, like editing input, formatting input, etc., formatting output, etc. We have the application logic layer, which is the layer where you would keep or code the business logic and the business rules and policies and procedures. This is what the users and the business stakeholders tell you they need to be implemented. And then there's data. Yeah. So data sometimes split into two layers, sometimes not. So in the data layer, in general, you may have a data manipulation layer that would have the logic of storing and retrieving data to and from the database, maybe things like maintaining integrity and so on. And finally, the actual data, we have you physically keep the data that belongs to a business or organization. I mean, we have 5 layers here, but you could also as easily regard them as 3 main layers, one to do with the data, yeah, one to do with the application and business logic, and one to do with presentation. Now we could subdivide these layers into other sublayers or other related layers to raise the maintainability and the flexibility of the system that we are trying to write. So this is like a nice summarizing diagram. We could have these layers. I'm not saying we have to have them. We could have these layers: data manipulation, application logic, presentation logic, and finally the actual presentations. The presentation layer would have the things to be actually displayed on the client. So generic client server architecture, but we're looking at what may make this up. and we could do it as a simple file server solution, or a client server solution where you actually have a dedicated server for some of these elements. So you might want to study that in a bit more detail and understand under each type of distribution how we might represent or place these particular layers that make up the application. So this is the client server solutions, where we have a two-tier of different types, like we could distribute the presentation, or we could distribute the data, or we have an N tier, i.e. more than 2 tiers, where we distribute the data and the application, possibly the presentation as well. So you can have a number of tiers in a client server, in a generic client server solution. The file server solution is not really a client server, and I'll show you why in a minute. But again, it's about where we place these things with respect to the overall application architecture. Or it could be complete network computing solution, where you have a free-for-all distribution. You can distribute the components wherever you like, but obviously you have to have a good network architecture behind you. And obviously, when you distribute things, you have many implications on performance, for example, on security, on availability. You have to think very carefully. So as I said repeatedly, this is your opportunity to design or build in certain non-functional and performance attributes into your software system. This is where you consider things like, what if the network goes down? What if there's a failure in one part of the system? What if I want to modify something or extend it? Maybe I have a high load of transactions or a very large volume of data. So how do I deal with that? Where do I have servers, and where do I place them? You may recall me saying last time something about Google servers and how they can easily scale up the system by adding more servers to the system to achieve speed and the ability to handle a very large volume of data and indices and so on. Okay, let me see what this says. Yeah. Okay. Right. The file server architecture is simply relies on a network of some sort, and you have a set of client computers, typically PCs, connected over a relatively short distance to one or more servers, and the function of these servers is just to bring you the files that you need, to bring the client the files that it needs. So the file server becomes something like a LAN, where you have one or more servers that keeps and hosts the data of an information systems. But all the other layers, all the other processing layers, are actually on the client computers. Yeah, so these are the computers that request that the files are brought or fetched to for processing, etc. But obviously, because you end up moving large chunks of data across the network to these clients, you have excessive network traffic. Yeah, you have a lot of load. Obviously, depends on how big the files are and how often you need to transfer these or transport the data between the client and servers. But this is a performance implication that you need to consider. The clients need to be fairly sort of strong, fairly robust, call them fat clients, because you have a lot of processing on these clients. Yeah, the clients do the processing, so they have to have the data fetched to them from the file server system, and they do the work there. Now, the database integrity can be compromised because whole tables have to be moved about, locked while a particular client is processing them. Yeah, you would have studied things about integrity in database systems, where we need to keep the correctness of the data sort of preserved without modifying the data values in a way that makes them inaccurate or out of sync with each other, because you have to move entire tables across. And while a particular client is processing this data, the file will need to be locked, and no one else can actually modified. So you can have, I'm sure you have studied these in more detail in database systems, whereby you lock a particular table and some transaction needs to be captured and reflected in the database, but the table is not available, and another client is waiting until the lock is released, etc., etc. Could lead to situations where the data is out of sync or is inaccurate. Right, file server architecture. This is a schematic that shows how this works. So we've got the file server here, yeah, and actually moves an entire table to a process that actually, this is a process that fetches the entire table and then passes it on to the client PC or computer for processing. So the file server here is just like a storage manager, yeah, and it locks the table while it's being charged out or locked out for the client until the client that is using this table returns it or releases the lock. And once the update has been effected, it checks in the tables back. Yeah, it stores the table back into the actual physical file and unlocks the table. Yeah, so this becomes like a guard on this data, but doesn't do any processing. The only processing it does is that it fetches the files, presents them or sends them to the client, and handles the locking and unlocking of the data. Yeah, so it provides, you can follow this in numbers. So one, the user requests something from the client, and the client issues a request to do something with the data, and this file server fetches the requested table, locks it, waits for this to finish its data. Obviously, it releases or passes on the data requested, and once the data is processed, it returns the entire table back to this file server, which then sends the updated table back to the database and unlocks the table. Very heavy network traffic here, yeah. As the table is fetched, it's passed to the processing application on the client, and then the entire table is returned back to the file server. The entire table is checked back into the database. You can imagine the traffic load that takes place in this particular situation. So this is about another definition of client-server architecture, similar to the one I gave you before, but here we can just take a look at the difference between a fat client and thin client. In fat client, you have like a heavy sort of a load-bearing, robust computer that actually does a lot of processing. So it is a personal computer or workstation that is rather powerful in the fat client situation, as opposed to the thin client, which could be simply just a browser. Yeah, so just a way of accessing the actual application that sits on a different server. So this does not have to be very powerful because it doesn't do any processing. It only handles the presentation of the user interface, accepting the user's commands and requests and mouse clicks and menu selections, etc., and it presents the data back to the user. So the only job it does is that it handles the presentation layer. As I said, this could be simply a browser, obviously with some kind of presentation logic as regards maybe authentication of the user, etc. So it doesn't have to be very powerful. Okay, I think I'll just leave you to read that. These are like types of servers. As I said earlier, the servers are like specialized component or machine or computer that specializes in serving a particular service or giving a particular service very efficiently and very fast, and where you concentrate all your particular performance boosting measures in a particular machine. So again, you're limiting the scope of the change or interest in a particular component into a single bundle or component. So your interest is not sort of distributed all over the place. You can optimize that. You can optimize the database server because this is the only job it does. You can optimize the transaction server because this is the only job it does. Yeah. So it's a server that hosts services which ensure that all database updates for a transaction succeed or fail as a whole. We have the concept of a transaction unit. So if something happens in between, the whole thing is repeated again because it makes sure that not half a transaction or part of a transaction only is executed, which would leave the database in a state that is lacking in its integrity. So this is part of an important part of the transaction server's job. Application server, which would host the actual application logic, etc., and so on and so forth. So we've got different types of servers that do different things. I need to say something here that something very important here, which is that the server does not necessarily have to be a hardware. It could actually be a software. An example is when you install a web server on your PC. Yeah, so you could get a web server software on your machine at home, and you make part of your machine at home your web server. Yeah, in fact, we all have print servers on our machines when we send particular files to be printed on the printer. So it could be just software that organizes and takes care of particular aspects of your work, like the database or the printing service or the application or the mail, etc. Okay, now we could have the client-server architecture, but in a way that distributes the presentation. Yeah, so the presentation and the presentation logic layers are shifted from the server to the client side. Yeah, so here we've taken the presentation out, we've put the presentation out on a client, as we saw in the case of a thin client, arrangement. So, yeah, this is good for integration with legacy systems. Like you have an old system that you want to, for example, make web enabled. So you write a layer to access the data or the application via a browser that sits on a thin client. Yeah, so this would be a nice way of dealing with the legacy system to upgrade it or modernize it by adding this layer at the client side to contain the presentation and the presentation logic, and the users get a fast and friendly and familiar interface to systems that maybe they have not been using anymore, or old systems that are not sort of compatible with the modern look and feel of modern systems. And the schematic representing it would be something like that. We've got the presentation logic residing here on the client. Yeah, so only the presentation logic gets executed on the client, but all the application logic and rules, etc., are residing on maybe a mainframe or another server here, and it could have like your legacy applications, etc. And you know, in the old days when you had systems like commercial systems written in COBOL, these were not web enabled, so you could interface the old system with a more modern presentation, GUI, and what have you, and things become more friendly and more familiar to the user. And at the back end here, you have the actual conventional files and the database. And what this mainframe does is it reads and writes into this database in the conventional way. So this bit is the conventional legacy system. That's how application used to be written in the past. The database and an application. Of course, we still have this, but this adds the top slice or the top layer of a web-enabled interface. Yeah, so it's a nice way or a trick or potential way of upgrading and modernizing your legacy systems. So here we mentioned distributed data, distributed presentation. We can also distribute the presentation. I'll leave you to read that, but this is how it would look like. Again, we've got the actual physical database, and we've got the data manipulation logic residing in the database server. So this would be like the access management system. Yeah. So here you would have your generalized database management system. That is accessing and updating and releasing and reading tables. So you have the data manipulation logic sitting on this component, the database server, and this database server serves the needed data by the client, and the client would have both the presentation and the application logic. Yeah. So we've only farmed out the data to the server side, but the client side still has the presentation logic and the application logic as well. So as you would have guessed it, this is not going to be a thin client. It's going to be a thick client with fairly robust processing power, because it has to run both the presentation as well as the application logic. So what have we distributed here? What became on the client, on the server side, I'm sorry, it's the data and it's manipulation logic. Yeah. So the part that is distributed, because I said, remember I said that the client server is a distributed system anyway, but you decide as to what you're going to distribute. So here we've decided to distribute the data. The problem is obviously with this particular arrangement is that if you have a number of clients, then you would have to duplicate the application or applications to the client. For example, if you have a large number of booking agents sitting at computers to book accommodation or airway tickets or whatever, and you have a pool of people who are doing these reservations, and you have this arrangement, you'll end up distributing the application on each of these clients. Obviously, it's not ideal for a number of reasons. So you find that actually the presentation logic is on a thin client, and the application logic is farmed out or is distributed to a specialized server, which would be an application server maybe sitting here in the middle. So we have this arrangement where you have a presentation logic only sitting on a client, thin client. Obviously, you don't need a very powerful one. And you have the application logic sitting on an application server, and the application server deals with the data server to access and manipulate and update the data. And this data manipulation server takes care of checking the tables out, reading the table, moving the tables about, and locking the various data, etc. Actually, I need to say something here, because in this particular arrangement, because you have the application logic sitting on a separate server, you would actually normally retrieve only the needed data, rows and columns from the table, not entire columns. Yeah, and you only lock the records and the data that are being processed that time by the application logic, and then it checks back the elements of the table that have been updated back to the database. So you can see here more flexibility. For example, if you need to update the applications, you don't have to go around a number of clients or a large number of clients to update the application. You only need to do it in one place, because all those clients access the application server, sending data and service requests and getting responses back. So it needs to be sitting only in one place. Obviously, there are performance requirements of this particular server. It has to be robust enough to be able to handle a number of requests from a number of clients. You know, the number of clients and number of requests obviously depends on what sort of application you're dealing with here. So there's a bit of performance engineering here, considerations for performance issues when you set this up. Sometimes even this application logic server, so the application server, you duplicate to achieve certain performance requirements. So you duplicate it, triplicate it, whatever. You have a number of servers that are cooperating to serve a large number of clients potentially. Okay. Now the internet or internet based architecture, where you rely heavily on the network, whether it's a local network or an external network, or network that can be accessed from the outside. So this kind of system is defined as a multi-tiered. So you've got a number of tiers, a multi-tiered solution in which the presentation and presentation logic layers are implemented in client-side web browsers using content downloaded from a web server. So you've got a web server, yeah. So these systems connect to a web server, and the presentation logic layer connects the application logic, and this application logic runs on the application server, which in its turn connects to the database server on sort of the backside or back end of the system. Now again, the great potential or advantage of this approach is that you can redesign traditional information systems to run on an intranet or an internet. Yeah, if we use the secure network that uses internet technology but accessed only from within the organization or particular group, we call this an intranet, not an internet. Yeah? So we use the same technology but to integrate our local work groups, our own desktops and machines, and enterprise computing elements, so that they're all accessed in an internet kind of fashion, but they're not available for use from the outside. So we call this an intranet. So you can use the same internet logic and technology and potentials to build our own system, which again has certain flexibility and robustness advantages. Let's look at a schematic for that. Okay, so let me enlarge that a bit. So that's the traditional thin client, which would have only web browser on it, only handles. This can be a very thin client, like a really very basic piece of equipment to just run the browser. And we have a web server that would handle the presentation logic. So actually the actual details of what the user can do once they've interacted with the browser. So it does things like it serves HTML page content, for example, or if it's data, then it's XML indexed or XML tagged data. And the browser simply sends to the web server its various commands, navigation, browsing, etc. If there are transactions as well, maybe filling forms, requesting authentications, etc. But these requests would not be processed on the client side. It's only the browser here. It's only the access, the superficial or the user side access. But the actual implementation of these requests would be via a web browser. So you've got the web browser that actually runs the executes the requests or the logic requested by the web browser. And here again we have the application logic flowing from the web browser. So the web browser does not have to keep the data itself. It calls upon an application logic. It does not have to actually process the or execute the business logic itself. It passes the request to the application server, which does that, and it sends back the information requested as well as the service responses. Now, this in turn deals with a database server, yeah, to the back of it, and this database server has the data manipulation logic as we saw in the other pattern. So this is even teasing out or separating out the components of the system onto further layers. So we started with 2 client server, then we started to distribute either the presentation or the data, and here we're distributing even the application. And if we go for an internet kind of technology, we could have 4, possibly more tiers here, a browser, presentation logic implemented on the web server, then application and data side, specialized servers as well. I want you to notice here, like in the reading and the locking, in this kind of system, I don't have to pass entire tables, but only the rows and columns that are needed. and then the locking and the release of the locks are on individual records and tables or columns or whatever you want to call them. And the result obviously is that the tables of database the databases are updated. Now I hope you see that we get more flexibility with these types of systems, with performance gains as well. Yeah, although performance gain is debatable. It depends on how you divide things up and the volumes of data that are being exchanged, the volumes of data and the frequency of transactions and the volume of transactions, etc., come into play here. Sometimes maybe you don't want this kind of distribution, different kind of distribution to achieve better performance or higher security. So you have to look at every case in its own right. You cannot assume that the more tiers you have, the better systems you have, for example. Yeah? You cannot make that assumption. You have to study the particular problem in hand. Okay, again, it's like this is another type of, it's the same type of N-tier architecture really, but just showing here a bit more details about what elements could reside on each type of client to server. So it's like similar to the one we've just seen, with more detailed like interactions and flows between these types of components. Now, I hope you see here that we're still looking at the software system at the high level of abstraction. We're not looking inside the internal logic of exactly how the presentation is given to the client in detail. We're not looking at how the web server is going to be serving various web services and various service requests. We're not looking into the internal or the details of the application logic inside here, neither for the data. We're just deciding that this is the overall arrangement. This is how we're going to cut up the application. Yeah, how many major components, where are these residing, and the various interactions between them and the types, because we want to reason about the various properties of the system. Like, does it serve the requirements that we have? Does it perform as we desire? What are the implications for security, for robustness, for flexibility, for extensibility, for response and performance, and things like that. Okay, I'll leave you to read that, just some examples. And here's just a quiz for you. In internet computing architecture, where does the presentation logic get executed? Yeah, where does the presentation logic get executed? We have to read the question very carefully. Yeah, where should we say the presentation logic layer is? Yeah, where does that reside? So something for you to think about. Okay. Again, these are things that you already know about. Different types of architectures, how you organize the data. So is it a relational database? Is it a distributed relational database? Or is it a distributed relational database management system? And we have modern types of databases like Hadoop, where we don't use the traditional table or relational model in organizing the data at all. Again, these are all major decisions that you have to make. Okay, now more generic templates, data processing systems, transaction processing applications, event processing systems, and language processing systems. Now, every type of these systems or applications would have typical application architectures that you might want to reuse for similar kinds of setups or environments. Okay. Application type examples. For example, the transaction processing system could be an e-commerce system, could be a reservation system, or whether it's for therapy or a clinic or accommodation or airway tickets, etc. Language processing systems need complete interaction time. So let's look at a couple of typical examples of transaction processing system which have these components. About the processing and application logic, transaction manager, and data. And the reason transaction manager is that transactions are often faced with a very high volume of transactions that have to be processed within specific amounts of time. So you have some performance constraints and tight constraints for turnaround time for the processing of these transactions. So you'd have like a specialized components to deal with these transactions. As I said, things like maintaining the integrity of applying the transactions. So you have minimum transaction size, for example, if it doesn't happen, if there's a breakdown or if there's an error or there's a malfunction, you have to keep a certain transaction unit to reverse or to go back to the beginning of and execute as one unit. Yeah, so the transaction manager will take care of this integrity preserving mechanism so that the database is not corrupted and the records do not lose their integrity. So this is a typical software architecture for an ATM system. It's fairly straightforward, and you would find it in your textbook as well. Right. I think I'll give you just to stop here very briefly and come back. So, trying to stop this recording. Okay. Sorry about this. I thought the recording had been stopped or paused. Just looking at some information systems architecture. As I said, some of them have a layered architecture, which include these sort of generic layers. We've seen these several times before. So we've got a user interface and user communication and something about managing or controlling the user interface, authentication, authorization, some presentation logic, and then a layer for information retrieval and modification, and then the actual transaction management database of the data manipulation and data access layers. Like for example, in the mental health care system, something like that, and it's accessed via a browser. So the presentation logic is implemented, or the presentation is basically a web browser, thin client, and you have all the logic for accessing the data and manipulating it here in the presentation logic layer. Something about user authentication and all the application logic as regards what actually happens with the data once it's transferred to and from the database, the patient database. Now, something important to say here is that this kind of architecture, in fact, I don't mean just the data architecture, any architecture that sort of separates out various bits of the system that differ by the rate of change, because, for example, the logging and authentication logic may be changed more frequently than the application logic and the business rules. So you separate them in a separate layer, because if you need to make a change to user roles and authentication and access and something about data validation, you don't actually have to reprogram or apply your basic business rules. And when you modify your business rules and interfere with business rules because something reasonably small or trivial has changed in another layer, you don't want to take too much time and effort doing it, and you don't want to risk introducing even more errors in the application layer, or the layer that has the business rules of this particular establishment that you're developing the software for. So the idea here is trying to localize the effect of change as much as possible. Really have to remember this. All these, many of these architectural styles aim to do just that, to localize the effect of change, so that the change does not have to be propagated to other parts of the system unnecessarily. That's why we're teasing out these categories of layers into, or categories of elements into layers in the system. Right, there's something here I'd like you to read in your own time about web-based information systems, because really many information systems and resources, data resources are managed and accessed via web-based systems, where the user interface is basically a web browser. More on these configurations of client-server architectures and how these might be organized are discussed in more detail in chapter 17, so you can look at that if you wish to see more examples and the reasoning for each example and the advantages and disadvantages. So that would be important. Well, we've seen that before. This just from Somerville's book, the difference between a thin client and a fat client. One has only the presentation layer, another has the presentation as well as the application processing. So I'll skip these. There are some explanation of each of these, the thin client model and the fat client model, and some more examples that I'd like you to read on your own. I don't want to take too much time now. Now, let's look at the key point of this lecture. So a software architecture is a description of how a software system is organized at a generic or a high level. Architectural design decisions include decisions on the type of application, the distribution of the system, and the architectural style to be used. Yeah. What do I mean by type of application? Is it an interactive system? Is it transaction-based system? Is it a batch system, etc.? And then you decide on various design options as a result of that particular decision. Very important to remember that the architecture, when you say the system architecture or the software architecture, we do not mean just a single diagram or single model. Usually we need a number of different models, because each model addresses a particular perspective or viewpoint, as I saw earlier. Like we saw in the Christian model, there's a conceptual view, there's a development view, there's a process view, and there's a logical view. How are you looking at this system? From what perspective, so that you document it from this perspective only, so as not to mix things together and keep the clarity of the situation, so that you can spot errors more easily and you can make sure that the views are integrated together more easily. Architectural patterns are a means of reusing knowledge about the generic system architecture, yeah, and they are a way of describing the architecture and explaining when it may be used and what advantages and disadvantages. So the patterns are like a nice aid for you to save you a lot of effort when it's suitable to do so. Like the generic architecture can suit a particular organization or development situation, but don't forget you always have to adapt and modify to suit the particular development problem better, or to fit it more better. Models of application systems architectures help us to understand and compare applications. Validate the design is very important. I said it several times, having a good discussion, a good debate with your stakeholders and your developers team, and to be able also to assess large-scale components for use, to reuse existing patterns and styles. Okay. transaction processing systems. I didn't speak very much about that, but he's like a little bit more about it. Transaction processing systems, or TPSs. This is another abbreviation that is used. Are interactive systems that allow information in the database to be remotely accessed and modified by a number of users. It's like you when you're withdrawing money from your ATM, from the ATM that accesses your account. Yeah. So these are all transactions. The point of sale systems, for example, all the sales from supermarkets, etc., are interactive systems because they update the databases more or less instantaneously, and the databases could be housed remotely from where the actual client is. Right, I didn't say very much about language processing systems. You can read about that. Translation and compilers and stuff like that. They would have, again, a slightly different type of architecture that is more suited to them. And again, you can use an architectural pattern or style, reuse it and parameterize it and adapt it as may be more fitting to your particular development situation. Okay, I'll stop here. I hope I haven't overrun by too much. I'd really like you to read these slides through and spend some time thinking about them and just venture forward and read more in the other chapters I mentioned and maybe other sources as well. And I'll see you all during the lecture time. Thank you very much. Be safe.